All right, let's get into it. Today, we're unpacking one of the most powerful tools in multivariable calculus, the chain rule. Honestly, this thing is your key to understanding how a change in one thing can send ripples through an entire system of connected variables.
You know what I'm talking about, right? Like when you push a single domino and a whole intricate pattern falls? Well, the multivariable chain rule is basically the math behind that chain reaction. It lets us calculate exactly how that first little push travels through a complex system.
So, here's our game plan. We're going to start with a quick refresher on the basics. Then, I'll introduce you to an awesome visual tool called the variable tree. From there, we'll build up the rule for two main cases, see it work with some real examples, and then finish up with a really cool shortcut that it makes possible. Okay, before we can understand the big, complex domino setup, we need to remember how the first one falls. So let's kick things off with a quick look back at the chain rule you already know.
You probably remember this guy from single variable calculus. It's pretty straightforward. If y depends on u and u depends on x, you just multiply the rates of change to see how x affects y. It's a nice, clean, one-way street of influence.
But what happens when life isn't so simple? In the multivariable world, things get way more interesting. Our main variable, let's call it z, might depend on two other variables, x and y. And then x and y could both depend on a single variable, t. So the question becomes, how does a little nudge in t ripple through both of these paths to ultimately affect z?
To wrap our heads around this, we need a map. And that's where this amazing tool called the variable tree comes into play. Seriously, this is going to make visualizing the flow of information so much easier. Okay, so let's build one. At the very top of the tree, think of it as the treetop, we have our final result, z. This is the thing whose change we're trying to figure out. Now, z doesn't just come from anywhere. It depends on x and y. So, from z, we draw two branches reaching down, one to x and one to y. These are our middlemen, our intermediate variables.
And at the very bottom, we have the root of it all, the source of the change, our independent variable, t. Since both x and y depend on t, we connect them. And just like that, we have a perfect map showing how change flows from the root, t, up through both branches to the top, z.
Now let's zoom in on this first situation. We'll call it case 1. This is where you have multiple paths but just one single variable at the bottom driving everything. And you know what's so cool about this? The main idea is incredibly simple. To find the total change in z that t causes, you just figure out how much change came through the x path, figure out how much change came through the y path, and you just add them together. That's it.
And that simple idea, well, it is the formula. Look at it. This first chunk right here, that's just the change via x path. And the second chunk, that's the change via y path. We just add them up. That's the multivariable chain rule for case 1. Not so scary now, is it? So, are you ready to level up? What happens if our variable tree gets even more complex? Welcome to case 2, where our intermediate variables, x and y, now depend on two different independent variables, say s and t.
Now, this might look like a lot, but don't get intimidated. The logic is exactly the same as before, we just have to do it twice. To find how z changes with respect to s, we just trace all the paths that start at s and add them up. Then, to find how z changes with respect to t, we do the exact same thing, but for all the paths starting from t. It's the same rule, just applied for each of our root variables.
Okay, enough theory. I think the best way to really nail this down is to get our hands dirty and actually see it work. So let's put these formulas to the test.
All right, let's walk through this first one together. We've got z equals x squared y, where x is t squared and y is t cubed. The goal is dz dt. Step 1, find the partials of z. The partial with respect to x is 2xy, and with respect to y is x squared. Easy enough. Step 2, find the derivatives along our paths. The derivative of x with respect to t is 2t, and for y it's 3t squared. Step 3, apply the formula. We just plug in all the pieces we just found. And finally, step 4, substitute and simplify. We swap the x and y back for their t expressions, do a little algebra, and bam! We get our final answer, 7t to the 6th power. But how do we know we're right? Well, for a simple one like this, we can actually check our work. If we just substitute for x and y at the very beginning, we find that z is just t to the 7th. And the derivative of that? It's 7t to the 6th. A perfect match! Love it when that happens. Okay, let's fire up a case 2 example.
This time, we only need to find the partial derivative of z with respect to s. The process is the same. First, find the partials of z with respect to x and y. Then, we find the partials of our paths x and y, but, and this is key, only with respect to s. We plug those pieces into our formula for del z over del s, combine the terms, and there's our final answer. Just remember, you're only following the trails that start from the variable you care about.
And now for the really fun part. Once you get comfortable with the multivariable chain rule, you unlock some seriously awesome shortcuts for other kind of annoying problems. Let's take a look at implicit differentiation.
You remember these, right? Trying to find dy dx when all the x's and y's are mixed together like this? The old way works, sure, but it can get pretty messy with all the rearranging.
Well, check out this beautiful shortcut that comes directly from the chain rule. First, you just move everything to one side of the equation so it equals 0, and call that whole thing f of x comma y. Then, dy dx is simply the negative of the partial derivative of f with respect to x divided by the partial of f with respect to y. It's so clean. Let's watch how fast this is. Step 1, find the partial with respect to x. Done. Step 2, find the partial with respect to y. Done. Step 3, just plug them into our formula, not forgetting that negative sign. A little bit of cleanup in step 4, and we have our answer. Way faster than the old method, right? That's the power of having the right tool.
So at the end of the day, this is about more than just some formulas. The chain rule is a framework for thinking about how interconnected systems work. It really makes you wonder, doesn't it? What other complex systems out there, in physics, in economics, even in biology, could we understand better if we could just map out their variable tree and trace how influence flows? Thanks so much for watching.